Now we're going to solve equations that involve logarithms. So like we use logarithms to simplify equations that involve exponentials, this time we will use exponentials to help us solve equations that involve logarithms. So the idea first is to get rid of this logarithm by exponentiating both sides. This word exponentiate means you make it a power of something. So we're going to make both sides powers of 2. So this became the power of 2 on the left side of the equation. This 5 became the power of 2 on the right side of the equation. Now why do we do that? Well, there's this property of logarithms we've learned. If you take b raised to a logarithm with the same base, they sort of cancel each other out. So 2 raised to the log base 2 of x just gives you x. And so this is an answer. X is 2 to the 5th, which you can simplify as 32. Let's look at a slightly more complicated example. This time I have log base 3 of a more complicated expression than just the variable, but we'll approach things the same way. The first thing we'll do is exponentiate both sides with the same base that's involved in the logarithm. That way we have 3 raised to a logarithm base 3. This quantity, this entire quantity, log base 3 of 4 to the x, became the exponent of 3 on the left side of the equation. This 2 became the exponent of 3 on the right side of the equation. Now a property of logarithms allows you to basically cancel the 3 raised to a logarithm base 3, leaving you with just 4 plus x. On the right side we have 3 squared, which of course simplifies to 9. And we can finish isolating now. If we subtract 4 from both sides of the equation, we get the exact answer, x equals 5. Here's another one. Solve a natural log of 3x equals 4. Now, remember, natural log is log base e. So if we want to be using the same base when we exponentiate, that base should be e. So e and the natural logarithm cancel each other out here, giving us 3x on the left side, e to the 4 on the right side. Isolate x by dividing both sides by 3. This is your exact answer, and if you evaluate that on a calculator, you can get a decimal approximation. X is approximately 18.2. And let's finish with one more example where we've got 2 logarithms showing up in the same equation. What we would really like to do is combine it into a single logarithm. And there's a property of logarithms that will let us do that. Remember, there's a property that says log of a minus log of b is equal to the logarithm of their quotient, a over b. And so that's what we're using here. Our x becomes the numerator and 5 becomes the denominator of this new logarithm. So now I've got a single logarithm. It's common log, so remember that's the same as log base 10. In order to undo that, I'm going to want to exponentiate both sides base 10. Now 10 raised to the log base 10 cancel each other out, giving us x over 5 on the left and 10 cubed on the right. And then you can simplify that, because if you multiply both sides by 5 and then rewrite 10 cubed as 1,000, 5 times 1,000 is 5,000, and that's an exact answer, an exact solution for this equation.